So good afternoon, January 22nd, 2015. This is MATB110, section 1, calculus 1. Today is day number 6 into week number 3. So let us get started. So first of all, good afternoon. Welcome back to this class, calculus 1. Today, if we can look at the calendar and also the user environment, is day number 6. And I read many of you have already made the submissions to your first homework assignment yesterday, both in a hard copy and also through the Moodle environment. I've already received 33 out of 36, so 3 of you did not submit it. Well, it's up to you. Now, if you have been paying attention to the coursework side, the reading for this week is very simple. Okay, you look at the reading for this week, which is released after our first class this week. It's on chapter 3, but not all of chapter 3, but on page 106 to 119, so the other half of chapter 3 will be next week's reading list. It's going to have a lot of very new things you're going to learn. All right, so at the end of that, I've also given you some intellect-based resources to answer 2 important questions. What is a calculus derivative? What is a calculus derivative? And also, what is calculus applications of derivatives? So many resources you can use to help yourself to understand the topics here. And I've also received questions on how best you can make your notes, that means to produce a journal. Well, essentially, I did not issue any very strict regulations yet. I mean, if you are very sincere in making notes for your own understanding, you can basically start with the textbook based on the reading list, and also based on 1 or 2 of these resources, or based on the reference text from Professor Hubert Strand from MIT OCW. Well, when you make a piece of note, don't try to make it too big at the very beginning. Make sure you do it point by point, based on perhaps the assignment, based on the quiz sections. Make sure on each section you make yourself understand it. And also, if you have been paying attention to my advice for this class, each week, particularly before the first day class, not before the Monday class, I have the before class activity for you. So the before class activity for week number 2 is here, and week number 3, I think it's actually week number 3, but I did not change the number here. Okay, maybe I'll change it immediately. Okay, now it's group number 3. Okay, we got it. So you can see that I have also given you practical chapters of the textbook, which is free of charge from Professor Gilbert Strand. All of these are section by section, so you can make notes according to your own schedule. But remember, we just collected them 4 times throughout the semester, so each time, be ready. We are not going to collect the notes after the deadline, so you have to wait until the next time, okay? And please make sure that make the best use of the excellent videos here from Khan's Academy. I know that many of you have some problems by just reading the textbook, so I would highly recommend that you come back to each one of the links here and watch some of the very interesting and practical videos here, particularly the squeeze theorem. Those of you ask me questions of how do we prove that limit of these theta approaching 0, sine theta over 0, theta is equal to 1. Well, study a little bit here, okay? So now, let me begin this week by asking you not this week, this class, by asking you the very important question. What have you learned on our Monday class? Remember? What have you learned on Monday class? Do you remember? Okay. Some examples. Okay, that's very good. Make you stay. For those of you who happen to forget, remember the class video is always here. You just click it and you can watch the whole class on Monday. All right? So don't forget it. Everything is here. Okay? And today's class will also be on YouTube by tomorrow. So let's get back to the business here. All right? Now we are very much interested in studying differential calculus. And when we talk about differential calculus, I invite you to study your section 1.5 in your chapter 1 of the textbook. And over there is a key question: what do we mean by the tangent? particular curve at a particular point, okay? So, and then this past Monday, we brought back Gilbert's-Brown to help you to understand with the highlight of calculus with the specific attentions on the meaning of derivative. And then we also invite David Jerison from Single Variable Calculus from MIT-OCW to help you with about 40 minutes, actually not 40, 28 minutes of his first lecture. In his lecture, he answered two questions, okay? You remember that. The first is, what is the derivative? Okay, what is the derivative? And he gave a geometric interpretations of what is a derivative. And the answer is page 54 of your textbook. Okay, if you have the textbook, and the answer is page 54 of the textbook. Define a tangent. Define a tangent at a particular point to a particular curve. So the geometric interpretations of the derivative is actually define the specific slope functions of a tangent line to a particular curve f of x at a particular point. Now, that is the geometric interpretation. And he said it's going to help us to understand it also through the physical interpretations. Today, I'm going to invite you to continue to understand this from Professor David Jerison. Okay? I would like to start up with the remaining of this last lecture, only 10 minutes, and then we're going to continue with the derivative lecture with a particular review on your second chapter. Again, David is going to provide us with something more about this. Now, in the meantime, in order to help you understand better calculus, I've also included 1, 2, 3 specific link on 3 different very interesting videos, which is a review of what we have been talking about. What is calculus? The birth of calculus. Who invented calculus? Remember, the two important persons. And calculus is the foundations of modern science. These are very important introductions for you to keep in mind and also not to lose the big picture. Okay? So, are we going to continue? Sure. Now, pay attention to what David has to say as a continuation of our last lecture.
So first of all, I want to give you a few more notations.
A few more notations.
And these are just other ways that people notations that people use to refer to derivatives. And the first one is the following. We already wrote y is equal to f of x, and so when we write delta y, that means the same thing as delta f. That's a typical notation. And previously, we wrote f prime for the derivative. So this is Newton's notation for the derivative.
Newton is
Okay.
right.
But there are other notations, and one of them is df dx, and another one is dy dx, meaning exactly the same thing. And sometimes we let the function slip down below, so that becomes dy dx of f, dy dx of y. So these are all notations that are used for the derivative, and these were initiated by Leibniz.
The second person who invented calculus.
These notations are used interchangeably, sometimes practically together. They both turn out to be extremely useful. This one omits, notice that this thing omits the underlying base point at 0. That's one of the nuisances. It doesn't give you all the information. But there are lots of situations like that where people leave out some of the important information. You have to fill it in from context. So that's another couple of notations. So now I have one more calculation for you today. I carried out this calculation of the derivative the derivative of the function 1 over x. I want to take care of some other powers. So let's do that. So example 2 is going to be the function f of x is x to the n equals 1, 2, 3, one of these guys.
It's a very important example.
And now what we're trying to figure out is the derivative with respect to x of x to the n in our new notation, what this is equal to. So, again, we're going to form this expression, delta f, delta x, and we're going to make some algebraic simplification. So what we plug in for delta f is x plus delta x to the n minus x to the n divided by delta x. Now before, let me just stick this in and I'm going to erase it. Before I wrote x0 here and x0 there. But now I'm going to get rid of it. Because in this particular calculation it's a nuisance. I don't have an x floating around, which means something different from the x0. And I just don't want to have to keep on writing all those symbols. It's a waste of Blackboard energy. There's a total amount of energy that I've already filled up so many Blackboards that it's just a limited amount of, plus I'm trying to conserve children. Okay, anyway, no zeros. So think of x as fixed. Again, in this case, delta x moves and x is fixed in this calculation. All right, now, in order to simplify this, in order to understand algebraically what's going on, I need to understand what the nth power of a sum is. And that's a famous formula. We only need a little tiny bit of it, called the binomial theorem. So the binomial theorem, which is in your text and explained in an exercise, says, in an appendix, sorry, says that if you take the sum of two guys and you take them to the nth power, that of course is x plus delta x multiplied by itself n times. And so the first term is x to the n. That's when all of the n factors come in. And then you could have this factor of delta x and all the rest x's. So at least one term of the form x to the n minus 1 times delta x. And how many times does that happen? Well, it happens when there's a factor from here, from the next factor, and so on and so on and so on. There's a total of n possible times that happens. And now, the great thing is that with this alone, all the rest of the terms are junk. That we won't have to worry about it. So, to be more specific, the junk, there's a very careful notation for the junk. The junk is what's called big O of delta x squared. What that means is that these are terms of order, so with delta x squared, delta x cubed, or higher. Right? That's how. Very exciting. Higher order terms. Okay. So, this is the only algebra that we need to do, and now we just need to combine it together to get our result. So, now I'm going to just carry out the cancellations that we need. So here we go. We have delta f over delta x, which remember was 1 over delta x times this, which is this, times, now this is x to the n plus n, x to the n minus 1 delta x, plus this junk term, minus x to the n. All right, so that's what we have so far based on our previous calculations. Now, I'm going to do the main cancellation, which is this. All right? So that's 1 over delta x times n, x to the n minus 1 delta x, plus this term here. And now I can divide in by delta x. So I get n x to the n minus 1 plus, now it's O of delta x. There's at least one factor of delta x, not two factors of delta x, because I have to cancel one of them. And now I can just take the limit. In the limit, this term is going to be 0. That's why I called it junk originally, because it disappears. And in math, junk is something that goes away. So this tends to, as delta x goes to 0, n x to the n minus 1. And so what I've shown you is that d by dx of x to the n minus, n, is equal to n x to the n minus 1. So now this is going to be super important to you, right on your problem set in every possible way. And I want to tell you one thing, one way in which it's very important, and one way that extends it immediately. So this thing extends to polynomials. We get quite a lot out of this one calculation. Namely, if I take d by dx of something like x cubed plus 5x to the 10th power, that's going to be equal to 3x squared. That's applying this rule to x cubed. And then here I'll get 5 times 10, so 50 x to the 9th. So this is the type of thing that we get out of it. And we're going to make more hay with that next time. I turned myself off. Yes? The question was, the binomial theorem only works when delta x goes to 0. No, the binomial theorem is a general formula which also specifies exactly what the junk is. It's very much more detailed. But we only needed this part. We didn't care what all these crazy terms were. It's junk for our purposes now because we don't happen to need any more than those first two terms. Yes, because the delta x goes to 0. Okay, see you next time.
Okay, now in this 10 minutes time, we're going to review something before we continue with the main lecture number 2. Okay, so first of all, at the beginning of the lecture, David said, we're going to learn what is meant by a derivative. And according to what we have been studying, the derivative is basically, with a geometric interpretation, is to find the slope function of a tangent line to a particular curve at a particular point. So we often use the delta y divided by delta x, or sometimes, as introduced in the notations here, with Newton's notation, which is f pi, with Michael's notation, it's d of y of x, right? So basically, this is the beginning of the story. And the second thing is, he introduced us, he would like to show us examples of differentiations. What is meant by differentiations is to how to do a differentiation, so differentiate a particular function, which is a given function, in order to obtain an explicit formula for the slope function, which is basically what you saw here with x to the power n. But interestingly, he's picked some problem which is generic enough for us to use for the applications of differentiations to the polynomial equations. So the x to the power n becomes n times x to the power n minus 1. That is the intermediate story. Okay? So what are we going to do now? Next, we need to remember.
The following content is provided in.
We need to remember from the perspective of the chapter 3, the derivative. Now, when we talk about geometry at the very beginning, in class number 1, day number 1, I introduced to you the definitions of calculus by helping you to understand different interpretations from the Wikipedia. At that time, we say, when we talk about geometry, we are talking about the inquiry about shape. When we talk about trigonometry, we are talking about the inquiry about the angles of a particular figure. And when we talk about calculus, it's basically about change. So that basis, and with so much of the interpretations given here, may I ask you one question? Is calculus more about averages or is calculus more about the rate of change? Which one is? You go for. Calculus is about average. Those of you who say yes, do raise your hand. Is calculus about averages? Okay, it's calculus about change. Can you raise your hand? Okay, so what about those who did not raise their hand? Okay, so with that as the basis, let us continue with lecture number 2, which is very much important.
For a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, so I'd like to begin the second lecture by reminding you what we did last time. So last time, we defined the derivative as a slope of a tangent line so that was our geometric point of view. And we also did a couple of computations. We worked out that the derivative of 1 over x was minus 1 over x squared. And we also computed the derivative of x to the nth power for n equals 1, 2, etc. And that turned out to be n x to the n minus 1. So that's what we did last time. And today, I want to finish up with other points of view on what a derivative is. So this is extremely important. It's almost the most important thing I'll be saying in class, but you'll have to think about it again when you start over and start using calculus in the real world. So again, we're talking about what is a derivative. And this is just a continuation of the last time. So as I said last time, we talked about geometric interpretations. And today, what we're going to talk about is rate of change as an interpretation of the derivative.
Rate of change.
So remember, we do graphic functions, y equals f of x, and we abstract the change in x, and here the change in y, let's say. And then, from this new point of view, a rate of change, keeping track of the rate of change of x and the rate of change of y, it's the relative rate of change we're interested in, and that's delta y over delta x. And it has another interpretation. This is the average change. And usually we would think of that if x were measuring time, and so the average, and that's when this becomes a rate. And the average is over the time interval delta x. And then the limiting value is denoted dy dx. And that is so this one is the average rate of change, and this one is the instantaneous rate.
You see the difference?
Okay, so that's the point of view that I'd like to discuss now and give you just a couple of examples. So let's see. Well, first of all, so maybe some examples from physics here. So Q is usually the name for a charge. And then dQ dt second example, which is probably the most tangible one, is we could denote the letter S by distance, and then the rate of change is what we call speed. So those are the two typical examples, and I want to illustrate the second example in a little bit more detail, because I think it's important to have some visceral sense of this notion of instantaneous speed. And I get to use the example of this very building to do that. Probably you know, or maybe you don't, that on Halloween there's an event that takes place in this building, or really from the top of this building, which is called the pumpkin drop. So let's illustrate this idea of rate of change with the pumpkin drop. So what happens is this building, well, let's see, here's the building. And here's the dot, that's the beautiful grass on this side of the building, okay? And then there's some people up here and very small objects. Well, they're not that small when you're close to them. They get dumped over the side there, and they fall down. That's, you know, everything at MIT, or a lot of things at MIT, are physics experiments. That's the pumpkin drop. So roughly speaking, actually this is, the building's about 300 feet high. We're down here on the first usable floor. And so we're going to use, instead of 300 feet, just for convenience purposes, we'll use 80 meters, because that makes the numbers come out simply. Okay, so we have the height, which starts out at 80 meters at time 0, and then the acceleration due to gravity gives you this formula for h. This is the height. So at time t equals 0, we're up at the top. H is 80 meters. So this is the net unit. And at time t equals 4, you notice 5 times 4 squared is 80. So I picked these numbers conveniently so that we're down at the bottom. Okay, so this notion of average change here, so the average change, or the average speed here, maybe we'll call it the average speed, since that's over this time that it takes for the pumpkin to drop, is going to be the change in h divided by the change in t, which is, it starts out at, what does it start out as? It starts out as 80, right? And it ends at 0. So actually we have to do it backwards. We have to take 0 minus 80, because the first value is the final position, and the second value is the initial position. And that's divided by 4 minus 0, time 4 seconds minus time 0 seconds. And so that, of course, is a minus 20 meters per second. So the average speed of this guy is 20 meters a second. Now, so why did I pick this example? Because, of course, the average, although interesting, is not really what anybody cares about who actually goes to the event. All we really care about is the instantaneous speed when it hits the pavement. And so that can be calculated at the bottom. So what's the instantaneous speed? That's the derivative. Or maybe I should, to be consistent with the notation I've been using so far, that's d by dt of h. Right? So that's d by dt of h. Now remember, we have formulas for these things. We can differentiate this function now. We did that yesterday. So we're going to take the rate of change, and if you take a look at it, it's just the rate of change of 80 is 0, minus the rate of change for this minus 5t squared, that's minus 10t. All right? So that's using the fact that d by dt of 80 is equal to 0, and d by dt of t squared is equal to 2t. The special case, well, I'm cheating here, but there's a special case that's obvious. I didn't throw it in over here. The case n equals 2 is that second case there, but the case n equals 0 also works. Because that's constants, the derivative of a constant is 0, and then the factor n there is 0, and that's consistent. And actually, if you look at the formula above it, you'll see that it's the case n equals minus 1. So we'll get a larger pattern soon enough with the powers. Okay, anyway, back over here, we have our rate of change, and this is what it is. And at the bottom, at the point of impact, we have t is equal to 4, and so h prime, which is the derivative, is equal to minus 40 meters per second. So it's twice as fast as the average speed here. And if you need to convert that, that's about 90 miles an hour, which is why the police are there at midnight on Halloween to make sure you're all safe, and also why when you come you have to be prepared to clean up afterwards. So anyway, that's what happens. It's 90 miles an hour. It's actually the building's a little taller, but there's air resistance. I'm sure you can do a much more thorough study of this example. All right, so now I want to give you a couple of more examples because time and these kinds of parameters and variables are not the only ones that are important for calculus. If it were only this kind of physics that was involved, then this would be a much more specialized subject than it is. And so I want to give you a couple of examples that don't involve time as a variable. So the third example I'll give here is the letter T often denotes temperature. And then dt dx would be what is known as the temperature gradient, which we really care about a lot when we're predicting the weather, because it's that temperature difference that causes airflows and causes things to change. And then there's another theme which is throughout the sciences and engineering, which I'm going to talk about under the heading sensitivity of measurements. So let me explain this. I don't want to belabor it because I just am doing this in order to introduce you to the ideas on your problem set, which is the first case of this. So on problem set 1, you have an example which is based on a simplified model of GPS, so the flat Earth model. And in that situation, well, the Earth is flat, it's just a horizontal line like this. And then you have a satellite, which is over here, preferably above the Earth. And the satellite knows exactly, or the system knows exactly where the point directly below the satellite is. So this point is treated as known. And I'm sitting here, okay, with my little GPS device, and I want to know where I am. And the way I locate where I am is I communicate with the satellite by radio signals, and I can measure this distance here, which is called h. And then the system will compute this horizontal distance, which is L. So in other words, what's measured, so h measured by radio waves and clock, various clocks, and then L is deduced from H. And what's critical in all of these systems is that you don't know H exactly. There's an error in H, which will denote delta H. There's some degree of uncertainty. The main uncertainty in GPS is from the ionosphere, but there are lots of corrections that are made of all kinds. And also, if you're inside a building, it's a problem to measure. But it's an extremely important issue, as I'll explain in a second. So the idea is we then get to the get at delta L is estimated by considering this ratio, delta L over delta H, which is going to be approximately the same as the derivative of L with respect to H. So this is the thing that's easy because, of course, it's calculus. Right? Calculus is the easy part, and that allows us to deduce something about the real world that's close by over here. But the reason why you should care about this quite a bit is that it's used all the time to land airplanes. And so you really do care that they actually know to within a few feet or even closer where your plane is and how high up it is and so forth. All right. So that's it for the general introduction to what a derivative is. I'm sure you'll be getting used to this in a lot of different contexts throughout the course. And now we have to get back down to some rigorous details. Okay? Everybody happy with what we got so far? Yeah. Good question. The question was, how did I get this equation for height? I just made it up because it's the formula from physics that you will learn when you take 801, and it has to do with the fact that if you, this is speed, if you differentiate another time, you get acceleration, and this is the acceleration due to gravity is 10 meters per second, which happens to be the second derivative of this. But anyway, I just pulled it out of a hat from your physics class. So you can just say C801. All right. Other questions? All right, so let's go on now. Now I have to be a little bit more systematic about limits. And so let's do that now. So now what I'd like to talk about is limits and continuity. And this is a warm-up for deriving all the rest of the formulas. All the rest of the formulas that I'm going to need to differentiate every function you know. Remember, that's our goal, and we only have about a week left. So we better get started. So first of all, there's what I will call easy limits. So what's an easy limit? An easy limit is something like the limit as x goes to 4 of x plus 3 over x squared plus 1. And with this kind of limit, all I have to do to evaluate it is to plug in x equals 4. Because, so what I get here is 4 plus 3 divided by 4 squared plus 1. And that's just 7 divided by 17. And that's the end. So those are the easy limits. Well, when you take a derivative, you're taking the limit as x goes to x0 of f of x, well, f of x, let's try, and all its work. Here's the formula for a derivative. Now notice that if you plug in x equals x0, always gives 0 over 0. So it just basically never works. So we always are going to need some cancellation. To make sense out of the limit. Now, in order to make things a little easier for myself to explain what's going on with limits, I need to introduce just one more piece of notation. What I'm going to introduce here is what's known as a left hand and a right hand limit. If I take the limit as x tends to x0 with a plus sign here of some function, this is what's known as the right hand limit. And I can display it visually. So what does this mean? It means practically the same thing as x tends to x0, except there's one more restriction which has to do with this plus sign, which is we're going from the plus side of x0. That means x is bigger than x0. And I say right hand, so there should be a hyphen here, right hand limit, because on the number line, if x0 is over here, the x is the x is to the right. All right, so that's the right-hand limit. And then this being the left side of the board, I'll put on the right side of the board the left limit. So that one has the minus sign here. I'm just a little dyslexic, and I hope you're not. So I may have gotten that wrong. So this is the left-hand limit. And I'll draw, so of course that just means x goes to x0, but x is to the left of x0. And again, on the number line, here's the x0, and the x is on the other side. Okay, so those two notations are going to help us to clarify a bunch of things. It's much more convenient to have this extra bit of description of limits than to just consider limits from both sides. Okay, so I want to give an example of this. And also an example of how you're going to think about these sorts of problems. So I'll take a function which has two different definitions. Say it's x plus 1 when x is bigger than 0, and minus x plus 2 when x is less than 0. All right, so we can put commas there. Those are, so when x is greater than 0, it's x plus 1. Now I can draw a picture of this. It's going to be kind of a little small, so I'm going to try to fit it down in here. Maybe I'll put the axis down below. So at height 1, I have, to the right, I have something at slope 1, so it goes up like this. All right? And then to the left of 0, I have something which has slope negative 1, but it hits the axis of 2, so it's up here. All right? So I have this sort of strange antenna figure here, which is my graph. Maybe I could draw these in another color. And then, if I calculate these two limits here, what I see is that the limit as x goes to 0 from above of f of x, that's the same as the limit as x goes to 0 of the formula here, x plus 1, which turns out to be 1. And if I take the limit from the, so that's the left-hand limit, that's this, sorry, yeah, I told you right. Which right, this is the right.
It's okay.
So it's that right hand. Here we go. So now I'm going from the left, and it's f of x. Again, but now, because I'm on that side, the thing I need to plug in is the other formula. Minus x plus 2, and that's going to give us 2. Now, notice that the left and right limits, and this is one little tiny subtlety, it's almost the only thing that I need you to really pay attention to a little bit right now, is that this, we did not need x equals 0 value. In fact, I never even told you what f of 0 was. If we stick it in, we could stick it in, okay, let's say we stick it in on this side. Let's make it be that it's on this side. So that means that this point is in, and this point is out. So that's a typical notation, this little open circle and this closed dot, for when you included the, so in that case, the value of f of x happens to be the same as its right-hand limit, meaning the value is 1 here, and not 2. Okay, so that's the first kind of example. Question? Okay, so now our next job is to introduce the definition of continuity. So that was the other topic here. So we're going to define f is continuous at x0 means that the limit of f of x as x tends to x0 is equal to f of x0. Right? So the reason why I spent all this time paying attention to the left and the right and so on and so forth, focusing, is that I want you to pay attention for one moment to what the content of this definition is. What it's saying is the following. So continuous at x0 has various ingredients here. So the first one is that this limit exists. And what that means is that there's an unlimited value both from the left and right. And they also have to be the same. All right, so that's what's going on here. And the second property is that f of x0 is defined. So I can't be in one of these situations where I haven't even specified what f of x0 is, and they're equal. Okay? So that's the situation. Now, again, let me emphasize a tricky part of the definition of a limit. This side, the left-hand side, is completely independent, is evaluated by a procedure which does not involve the right-hand side. These are separate things. This one is to evaluate it. You always avoid the limit point. So that's, if you like, a paradox, because it's exactly the question is it true that if you plug in x0, you get the same answer as if you move in the limit? That's the issue we're considering here. We have to make that distinction in order to say that these are two, otherwise this is just tautological. It's a very little, it doesn't have any meaning. But in fact, it does have meaning because one thing is evaluated separately with reference to all the other points. And the the other is evaluated right at the point in question. And indeed, what these things are exactly the easy limits. That's exactly what we're talking about here. They're the ones that you can evaluate this way. So we have to make the distinction, and these other ones are going to be the ones that you can't evaluate that way. So these are the nice ones, and that's why we care about them, why we have a whole definition. All right. So now what's next? Well, I need to give you a little tour, a very brief tour of the zoo of what are known as discontinuous functions. So sort of everything else that's not continuous. So the first example here, let me just write it down here, is jump discontinuities. So what would a jump discontinuity be? Well, we've actually already seen it. The jump discontinuity is the example that we had right there. This is when the limit from the left, and right exist, but are not equal. Okay, so that's as in the example. Right, in this example, the two limits, one of them was 1 and one of them was 2. So that's a jump discontinuity. And this kind of issue of whether something is continuous or not is may seem a little bit technical, but it is true that that people have worried about it a lot. Bob Merton, who was a professor at MIT when he did his work for the Nobel Prize in economics, was interested in this very issue of whether stock prices of various kinds are continuous from the left or right in a certain model. And that was a very serious issue in developing the model that priced things that hedge funds use all the time now. So left and right really can mean something very different. In this case, left is the past and right is the future. And it makes a big difference whether things are continuous from the left or continuous from the right. Right, is it true that the point is here, somewhere in the middle, somewhere else? That's a serious issue. So, the next example that I want to give you is a little bit more subtle. It's what's known as a removable discontinuity. And so what this means is that the limit from left and right are equal. So a picture of that would be you have a function which is coming along like this, and there's a hole maybe where, who knows, either the function is undefined or maybe it's defined up here, and then it just continues on. All right, so the two limits are the same. And then, of course, the function is begging to be redefined so that we remove that hole. And that's why it's called a removable discontinuity. Now let me give you an example of this, or actually a couple of examples. So these are quite important examples which we'll be working with in just a few minutes. So the first is the function g of x, which is sine x over x. And the second will be the function h of x, which is 1 minus cosine x over x. So we have a problem at g of 0. G of 0 is undefined. On the other hand, it turns out that this function has what's called a removable singularity, namely the limit as x goes to 0 of sine x over x does exist. In fact, it's equal to 1. So that's a very important limit that we'll work out either at the end of this lecture or the beginning of next lecture. And similarly, the limit at 1 minus cosine x divided by x goes to 0, is 0. Okay, so these are very useful facts that we're going to need later on. And what they say is that these things have removable singularities. Sorry, removable discontinuity. All right, so as I say, we'll get to that in a few minutes. Okay, so are there any questions before I move on? Yeah. The question is, why is this true? Is that what your question is? The answer is, it's very, very unobvious. I haven't shown it to you yet. And if you were not surprised by it, then that would be very strange indeed. So we haven't done it yet. You have to stay tuned until we do. Okay? We haven't shown it yet. And actually, even this other statement, which maybe seems stranger still, is also not yet explained. Okay? So we're going to get there, as I said, either at the end of this lecture or at the beginning of next. Other questions? All right, so let me just continue my tour of the zoo of discontinuities. And I guess I want to illustrate something with the convenience of right and left-hand limits. So I'll say this board about right and left-hand limits. So a third type of discontinuity is what's known as an infinite discontinuity. And we've already encountered one of these. I'm going to draw them over here. Remember, the function y is 1 over x. That's this function here. But now I'd like to draw also the other branch of the graph of the hyperbola down here and allow myself to consider negative values of x. So here's the graph of 1 over x. And the convenience here of the distinguishing the left and the right-hand limits is very important, because here I can write down that the limit as x goes to 0 plus of 1 over x. Well, that's coming from the right, and it's going up. So this limit is infinity. Whereas the limit in the other direction, from the left, that one is going down. And so it's quite different. It's minus infinity. Now, some people say that these limits are undefined, but actually they're going in some very definite direction. So you should, whenever possible, specify what these limits are. On the other hand, the statement that the limit as x goes to 0 of 1 over x is infinity is simply wrong. Okay? It's not that people don't write this. It's just that it's wrong. It's not that they don't write it down. I mean, in fact, you'll probably see it. It's because people are just thinking of the right-hand branch. It's not that they're making a mistake necessarily, but anyway, it's sloppy. And there's some sloppiness that will endure and others that will try to avoid. So here, you want to say this, and it does make a difference. You know, plus infinity is a infinite number of dollars, and minus infinity is an infinite amount of debt. They're actually different, they're not the same. So, you know, this is sloppy and this is actually more correct. Okay, so now in addition, I just want to point out one more thing. Remember, we calculated the derivative, and that was minus 1 over x squared. But I want to draw the graph of that and make a few comments about it. So I'm going to draw the graph directly underneath the graph of the function. And notice what this graph is. It goes like this. It's always negative, and it points down. So now this may look a little strange, that the derivative of this thing is this guy, but that's because of something that's very important. We should always remember this about derivatives. The derivative of a function looks nothing like the function necessarily. So we should just forget about that as being an idea. Some people feel like if one thing goes down, the other thing has to go down. Just forget that intuition is wrong. What we're dealing with here, if you remember, is the slope. So if you have a slope here, that corresponds to just a place over here. And as the slope gets a little bit less steep, that's why we're approaching the horizontal axis. We're getting the number's getting a little smaller as we close in. Now over here, the slope is also negative. It's going down. And as we get down here, it's getting more and more negative. As we go here, the slope, this function is going up, but its slope is going down. All right, so the slope is down on both sides. And the notation that we use for that is well suited to this left and right business. Namely, the limit as x goes to 0 of negative 1 over x squared, that's going to be equal to minus infinity, and that applies to x going to 0 plus and x going to 0 minus. So both at this property. Finally, let me just make one last comment about these two graphs. This function here is an odd function. And when you take the derivative of an odd function, you always get an even function. And that's closely related to the fact that this 1 over x is an odd power in this 2. X to the first power is an odd power, and x squared is an even power. So all of your intuition should be reinforcing the fact that these pictures look right. Okay, now there's one last kind of discontinuity that I want to mention briefly, which I will call other. Ugly discontinuities. And there are lots and lots of them. And so one example would be the function y is equal to sine 1 over x as x goes to 0. And that looks a little bit like this. Back and forth and back and forth. It oscillates infinitely often as we tend to 0. And there's no left or right limit in this case. So there is a very large quantity of things like that. Fortunately, we're not going to deal with them in this course. A lot of times in real life, there are things that oscillate as time goes through things, but we're not going to worry about that right now.
I think we need to stop here.
So that's our.
You can continue to watch the remaining 8 minutes with you perform, coming back to the course side. But do not forget that in the context of your class material, I've given you some very good review material on the limits, which is on the chapter 2. Okay, allow me to take attendance today, and then watch for after-class activity, which is going to be released tomorrow, which is going to prepare you for next week's work. Okay. So, Nikki, are you here today? Thank you. Tori, thank you. And then Eden, thank you. Jason, thank you. Kurtwin, thank you. Roy, thank you. Amy, thank you. And then Susie, thank you. Bob, thank you. Vivian, thank you. Son, thank you. Mitchell, thank you. Luana, thank you. Sue, here, not here, okay. Pete, thank you. And then Elaine, thank you. Ken, thank you. Elvis, thank you. And then Anson, thank you. Caesar, thank you. Alex, thank you. Kinda, okay, thank you. Garjun, thank you. Yes, after roll call, you can go to the next class. Sinha, are you here? No, okay. Hinge, thank you. Simon, not here?
Yeah.
Oh, thank you. All right, so William, thank you. And then Sting, yes. Esther, thank you. Ida, is it Ida? Okay, thank you. Thank you. Ming, thank you. Flora, thank you. Just a minute, okay. Logo, thank you. Jackie, thank you. Amber, thank you. And then finally Kay, thank you. Yes, what can I do? You're the key. It's all right, let me go back. Which one? Sure. Oh, thank you very much. All right, so make sure you pay attention to the after-class activity to be released tomorrow. It's going to help you a lot, okay? Thank you. Now let me close the camera first. Okay, that's it for today's MATB 110, Section 1, Calculus 1, on January the 22nd, 2015, okay?